The natural world, in all its beauty and complexity, is built upon invisible building blocks. These building blocks are the foundation of everything we see around us, from the tallest mountains to the smallest grains of sand. They form the intricate patterns in nature, the diverse ecosystems that thrive on our planet, and the very essence of life itself. These are atoms, the tiny particles that make up everything we see and feel. Atoms are the fundamental units of matter, the smallest pieces that retain the properties of an element. They are so small that millions of them could fit on the head of a pin, yet they are the building blocks of the entire universe. But even an atom, small as it is, has its own internal structure. Within each atom lies a complex arrangement of subatomic particles, each playing a crucial role in the atom's behavior and characteristics. This internal structure is what gives each element its unique properties and allows for the vast diversity of matter in the universe. At its very core lies the nucleus, a region of immense density and energy. The nucleus is composed of protons and neutrons tightly bound together by powerful nuclear forces. This tiny core is incredibly dense, containing nearly all of the atom's mass, and it is the source of the atom's energy and stability. This nucleus is the heart of the atom, dictating its properties and determining its place in the grand scheme of elements. The number of protons in the nucleus defines the element, while the arrangement of electrons around the nucleus influences the atom's chemical behavior. Together, these factors determine how atoms interact with each other and form the diverse materials that make up our world. To understand the workings of the universe, we must first delve into this microscopic realm and unravel the secrets of nuclear physics. Nuclear physics is the study of the forces and interactions that govern the behavior of atomic nuclei. By exploring this field, scientists can uncover the fundamental principles that drive the universe and gain insights into the nature of matter and energy. This field of science, a journey into the heart of matter, reveals forces of unimaginable power and processes that defy our everyday experience. Nuclear reactions, such as fusion and fission, release vast amounts of energy, powering stars and providing the potential for advanced energy sources on Earth. These reactions also play a crucial role in the formation of elements, shaping the very fabric of the cosmos. Yet these very forces and processes are the architects of our universe, shaping the stars above and the very elements that make life possible. The elements formed in the hearts of stars are scattered across the universe, eventually becoming the building blocks of planets, plants, animals, and humans. The study of nuclear physics not only helps us understand the universe's past, but also guides us in exploring its future. Our exploration begins with the nucleus itself, a cluster of particles bound together with incredible strength. By studying the nucleus, we can unlock the mysteries of the atomic world and gain a deeper appreciation for the forces that shape our reality. This journey into the heart of the atom is a testament to human curiosity and our relentless pursuit of knowledge. The nucleus of an atom is a bustling hub of activity, home to two primary particles, protons and neutrons. These particles are fundamental to the structure of matter and play a crucial role in the behavior of atoms. Protons, positively charged, give the nucleus its overall positive charge. This positive charge is not just a trivial detail, it is essential for the atom's identity and interactions. This positive charge is crucial, for it dictates how the atom interacts with the negatively charged electrons that orbit the nucleus. These interactions are the foundation of chemical bonds and reactions, which are the basis of chemistry and biology. Neutrons, as their name suggests, carry no charge, making them electrically neutral. Despite their lack of charge, neutrons are indispensable to the nucleus. But their presence is vital, for they contribute to the stability of the nucleus and influence the atom's mass. Without neutrons, the repulsive forces between protons would cause the nucleus to fly apart. Together, protons and neutrons, collectively known as nucleons, determine the identity of an atom. The balance and number of these nucleons are what make each element unique. The number of protons, known as the atomic number, defines what element an atom represents. This atomic number is a fundamental property that distinguishes one element from another. For example, an atom with 1 proton is always hydrogen, while an atom with 6 protons is always carbon. This simple yet profound difference in proton number leads to vastly different chemical properties and behaviors. The combined number of protons and neutrons determines the atom's atomic mass, a measure of its heaviness. This mass is crucial for understanding the atom's stability and how it will interact with other atoms. It is within this tiny, densely packed nucleus that the story of nuclear physics truly unfolds. The interactions and forces at play here are the key to understanding not just the atom, but the universe itself. From the energy that powers the sun to the elements that make up our bodies, the nucleus is at the heart of it all. One might wonder, how can a nucleus, packed with positively charged protons, remain stable? After all, like charges repel, and the protons should push each other apart. The answer lies in a fundamental force of nature, the strong nuclear force. This force, one of the 4 fundamental forces in the universe, is immensely powerful, far stronger than the electromagnetic force that governs the repulsion between like charges. The strong force acts over incredibly short distances, binding protons and neutrons together within the incredibly small confines of the nucleus. It is this delicate balance between the repulsive electromagnetic force and the attractive strong force that dictates the stability of an atom's nucleus. The strong force is a force of immense consequence, for it is the very glue that holds the universe together at its most fundamental level. Without it, atoms as we know them could not exist, and the building blocks of matter would be scattered across the cosmos. Section 4, Stable and Unstable, the Dance of Radioactivity. Not all nuclei are created equal. Some are inherently stable, their protons and neutrons locked in a harmonious balance. Others are unstable, their internal forces in a state of tension prone to decay and transformation. This process of decay, known as radioactivity, is a fundamental aspect of nuclear physics. Radioactive nuclei emit particles and energy in an effort to achieve stability, transforming themselves into different elements in the process. This transformation, a kind of nuclear alchemy, occurs at a predictable rate, known as the half-life. Each radioactive isotope, a variant of an element with a specific number of neutrons, has a unique half-life, ranging from fractions of a second to billions of years. This dance of decay, while seemingly chaotic, is governed by strict physical laws, and its study has unlocked a wealth of knowledge about the nature of matter and the history of our universe. Section 5. Nuclear reactions, fission and fusion. In this section, we delve into the fascinating world of nuclear reactions, exploring the 2 primary processes that release vast amounts of energy, fission and fusion. While radioactivity involves the spontaneous decay of unstable nuclei, releasing particles and energy in the process, nuclear reactions, on the other hand, involve the deliberate manipulation of atomic nuclei to release even greater amounts of energy. These reactions are not random but are carefully controlled to harness their immense power. 2 types of nuclear reactions are of paramount importance in both scientific research and practical applications: fission and fusion. Each of these processes has unique characteristics and potential uses. Nuclear fission, as the name suggests, involves the splitting of a heavy nucleus, such as uranium or plutonium, into lighter nuclei. This process is initiated when a heavy nucleus absorbs a neutron, becoming unstable and breaking apart. This splitting is typically induced by bombarding the heavy nucleus with neutrons, which causes it to become unstable and split into 2 or more smaller nuclei, along with a few free neutrons and a large amount of energy. The free neutrons released can then go on to induce fission in other nearby nuclei, triggering a chain reaction that releases tremendous energy. This chain reaction is the principle behind nuclear reactors and atomic bombs. Nuclear fusion, on the other hand, involves the fusing or combining of light nuclei, such as hydrogen isotopes, to form heavier nuclei, such as helium. This process is the opposite of fission and requires extremely high temperatures and pressures to overcome the repulsive forces between the positively charged nuclei. When these light nuclei fuse, they form a heavier nucleus and release a tremendous amount of energy. This is the same process that powers the Sun and other stars, providing the energy that sustains life on Earth. This process, the very engine that powers the Sun and other stars, releases even greater amounts of energy than fission. The potential of fusion as a nearly limitless and clean energy source has driven scientific research for decades. Both fission and fusion hold immense potential as sources of energy. Fission is already widely used in nuclear power plants to generate electricity, while fusion remains a goal for future energy production due to its promise of abundant and clean energy. However, both processes present significant technological challenges. Fission reactors require careful control to prevent accidents and manage radioactive waste, while achieving the conditions necessary for sustained fusion reactions has proven to be a formidable scientific and engineering challenge. Harnessing the power of the atom for peaceful purposes has been a defining challenge of the 20th and 21st centuries. From the development of nuclear power plants to the ongoing quest for practical fusion energy, the journey of mastering nuclear reactions continues to shape our world and our future.